Good afternoon, everybody. I wanna go discussion on the XPS, that means X-ray Photoelectron Spectroscopy. It's a very good tool for surface analysis. First of all, I want to discuss on the background of this XPS. XPS techniques is based on Einstein's idea about the photoelectron effect developed around 1905. The concept of photon was used to describe the ejection of electron from the surface when photons are impinged upon it. During mid-1960s, Professor Keijan and his research group developed the XPS technique. For this reason, 1981, he was awarded the Nobel Prize in Physics for the development of XPS techniques. Before going to discuss about XPS, we have to know about something, the structure of solid, because XPS tools or techniques are very related with surface chemistry of a matter. First of all, Fermi level and energy band structure of solid. In this case, the left figure shows viewpoint of electronic structure. In this case, this is the inner core electronic configuration of palladium, and that right one viewpoint of energy. Here the core level, band, valence band and conduction band, and this is the energy. And the right side figure shows that energy band structure of solids. Look at here, the top of this figure, the conduction band and the valence band. Between these two, there is a Fermi level, and the topmost of this figure, no electron in conduction band. This is the back end, and the below of this figure, right figure below, this is the conductance of electrons in solid. Fermi level and energy band structure of solids. What is Fermi level? Fermi level is the term used to describe the top of collection of electron energy levels at absolute zero temperature. Look at here, at absolute zero temperature, and this is the Fermi level. And another, the Fermi level is the surface of that sheet at absolute zero, where no electrons will have enough energy to rise above the surface. And band gap is the energy difference between the valence band and the conduction band.
So, I am familiar with this. If you don't know, please ask. Okay.
So in this case, this figure shows about this. This is a summary of this. This one, E gap, that means band gap, and this level, this is the Fermi level, and this one, the topmost, this one, this is the conduction band, and this is the valence band, and between this is the Fermi level and the band gap. Sometimes people make a mistake. The Fermi level and the band gap are very similar, but a little bit different. It means that the Fermi level, this is the valence band high level or the topmost level, and energy band structure of solids. If we compare the insulator, semiconductor and the conductor, look at here, the left figure, number A, shows the insulator, middle one, semiconductor, and the last one, that means the right side one, conductor. The insulator, the large energy gap between the valence and the conduction bands in an insulator, it said that the ordinary temperature, no electrons can reach the conduction band. It means that the valence band and the conduction band, there is a very big gap. This is the Fermi level in gap. And another two, that means semiconductor and the conductor. In this case, in semiconductors, the band gap is small enough that thermal energy can bridge the gap for a small fraction of electrons. That means this level. In conductors, that means in right side in conductors, there is no band gap since the valence band overlapped to the conduction band. It means this is the overlapping between valence band and the conduction band. Next, relationship between energy band and XPS. It means that given energy band drive the XPS spectra, given XPS spectra drive the energy band. It means it's are interrelated. Energy band structure, this figure, the below figure, energy band structure of solids. This is the vacuum level, EV, Fermi level. In this case, the binding energy EV, that means this one, this is the EV, binding energy EV is the energy for binding electrons from a core level to Fermi level. This is the core level and this is the Fermi level. Between core level and Fermi level, this is the EV. And binding energy phi S is the energy between the vacuum level and Fermi level. This is the vacuum level and Fermi level. For example, an electron which stays in the core level of S1s can be ejected out for the sample surface and it becomes a free electrons with a kinetic energy Ek, and in this case from point A to B on the way, it means this is the H nu. This H nu actually the Einstein come from the Einstein theory. It means H nu equal to, we know that, binding energy plus kinetic energy.
What does it mean the vacuum level?
Vacuum level, EV, vacuum level, that means this is the energy. For example, look at here, this is number A. You consider if the core level of 1s, the electron can be come out from the surface. The vacuum level, this vacuum level, that means there is no energy. It means that the free energy or the without, I mean that, look at here, vacuum level actually, this is the energy gap level, there is no valence band or something like that, this area.
전자가 아예 방출되어서 날아가는 상태의 방식 같은데
쟤 지금 뭐라고 생각하는 거예요? Can you go back?
페르미 레벨 위에 있는 데로 말한 것 같은데요.
Can you go back? What? Can you explain again what you said? The vacuum level?
Vacuum level, this is the Fermi level, and above the Fermi level, vacuum level, EV, binding energy is the energy. This is the energy level. Actually, all are energy level for binding electrons from a core level to Fermi level. The binding energy level and vacuum level. It means that this is the vacuum level. It means that the one of the binding energy states this is the level of the I mean, if we consider this one, for example, this is the Fermi level. For example, in this case, this is the Fermi level. The Fermi level and the energy gap. I said to you that the energy gap, conduction band and the valence band, between the conduction band and the valence band, this is the energy gap. And Fermi level is the highest or topmost level of the valence band.
And lowest level of conduction band.
Yes, and this point, I mean that the vacuum level, this is the vacuum level.
제가 이해하는 게 영어로 설명하기가 좀 힘들 것 같은데 XPS를 측정하면 전자를 소분해서 고주의 전자 방출되는 거에 키네틱 에너지를 측정해서 그 원소의 오비탈 에너지를 계산하는 거잖아요. 이게 주어는 에너지는 다 똑같으니까 그게 에너지가 이제 튀어나와서 그 검출기로 들어갈 때 그게 주는 에너지는 다 똑같은데 나오는 에너지는 다 다르졌습니다. 그 나온 에너지가 방출기로 들어갈 때 키네틱 에너지를 역으로 추산해서 이 바인딩 에너지를 계산하는 걸로 알고 있는데, 그래서 제가 생각하기에 백중 레벨은 튀어나오려고 주는 에너지거나 튀어나온 다음에 움직이는
전자가 완전히 튀어나가는 상태지.
예, 저는 그렇게 생각을 하고 있는데
제가 말하는 걸 내가 무슨 얘기인지 모르겠는데
그렇게 저걸 이해를 하게 힘든 것 같아요.
We don't understand your point. I mean, the vacuum level. It says here the vacuum level is the level from the electron from the core is after ejected fully. So there is no electron. That is the vacuum level. We don't understand what you're talking about. It says here the vacuum level is from the lowest energy. When it obtains the energy, the electrons is fully ejected, so there is no electron. That is vacuum level.
Can I tell something? Actually, if we consider this Fermi level, up to Fermi level, electron can come back to our actual position, but when it goes out to vacuum level, this fully ejected, there is no withdrawal. It just go as like a photoelectronic spectrum. When its electron goes out, it cannot come down. It's fully out. That is the vacuum level.
Why are you explaining this the vacuum level and Fermi level?
Because in this spectra, this is interrelated with the surface.
And you're going to talk about the Oja electron as well?
Yeah.
Okay, go ahead. 컴퓨터는 만드는 거야?
Can I try?
리스타트 컴퓨터 아닌데.
국주는 그렇게 바쁠 이유가 없는데 뭐 카메라를 하고 너무 뜨는데?
다른 것도 있고 집에 컴퓨터가 좀 안 되고.
아 그래?
컴퓨터 좀
내가 언제 나올지를 모르겠는데 나도 저기 처할 때가 갔다 왔는데 내가 너 논문을 이번 연휴 때 좀 작업을 했으면 좋겠는데
저 월요일까지는
아직 다 안 했어?
레퍼런스가 아직 레퍼런스를
레퍼런스는 괜찮아. 그럼 나중에 해줘.
레퍼런스가 맞춰서
오케이, go
And what is XPS? Hajiband developed XPS in 1950 to 1960. He won the Nobel Prize in 1981 for significant contribution to photoelectronic spectroscopy. Already I will discuss. And in this case, XPS means X-ray photoelectronic spectroscopy. Its another name is ESCA, electron spectroscopy for chemical analysis. And primary beam X-ray and X-ray source there are various or several types of source. For example, Al, K alpha, photon 1486.7 eV, emitted signal electrons, sampling depth normally 10 nanometer, and beam size typically several millimeter for monochromated X-ray source, and focus X-ray beam 10 micrometer in diameter. And this is the X-ray photoelectron spectroscopy. In this case, I try to discuss only this equation. This equation is the binding energy for the core electron is given by the Einstein relationship. H nu equal to EB plus EK and phi, where H nu is the X-ray photon energy for L, K, H nu equal to 1486.6 eV. K is the kinetic energy of the photoelectrons, which can be measured by the energy analyzer, and phi is the work function. And by the analyzer about 4 to 5 eV. And this is the diagram. This is the diagram shows that the X-ray, this is incident X-ray, and this is the photoelectron. And normally this is the sample, and in this case we know that the XPS can measure only about 10 nanometer depth of the surface. And can you
Hold on. Can you go back? So what are you measuring?
In this case, this is the sample. I say that the X-ray, that means the this is the X-ray. This means the incident electron come from here, and
So, yeah, you're applying the HANU, so X-ray. So this is the coming incident energy, and that is applied to your material, the atom, and what are you measuring?
I mean that this is a sample, and in this case, while the photoelectron, this one is this beam, X-ray beam. This one is the incident X-ray in this case, and this is the sample. And sample in this case, it shows that approximately 10 nanometer.
Don't repeat, please. Yeah, that we heard. So you're applying incident HANU, right? With that energy, and that energy is subjected. Your material, your atom is subjected. Your compound is subjected to the incident energy with HANU, and what are you measuring?
And in this case, the detector can detect the kinetic. This is the kinetic energy.
What kind of kinetic energy?
The kinetic energy, okay, I will show later. The kinetic energy. For example, look at here. This is total H nu, and this part, this is the binding energy, and this one the kinetic energy. So there are several types of I can discuss this one later. If you don't understand, then I will discuss this later. So first, capability of the XPS, the identification of the elements contained in the sample, analysis of chemical status of the elements, quantification of chemical compositions, destructive depth profiling with an anagram, non-destructive depth profiling, neutralization of surface charging, and the chemical imaging. This is the capability. and basic principle of XPS. An alternative approach is to consider a one electron model. If we consider one electron model along the line of the following picture, in this case, look at here, this is the initial state and this is the final state. In this case, the binding energy is now taken to be a direct measure of the energy required to just remove the electron. The first, remove the electron, I mean that the H nu, and then connect it from its initial level to vacuum level, and the binding energy of the photoelectron is again given by EB equal to H nu minus EK. I don't know if you understand or not. It means that if we apply the X-ray, that means the energy H nu, then one electron can goes out and it can release the energy, and this energy we can calculate by this equation. That means EB equal to H nu minus EK. So in this case, H nu, we know that this is the this comes from the Einstein equation, EB and EK. This is the binding energy and another one is kinetic energy.
얘가 지금 말하려고 그러는 거는 이게 엑스레이를 때린 다음에 여기에서 바인딩 그 백큐 레벨까지 올라오는 잡혀 있는 바인딩 에너지를 벗어난 거에 키네틱 에너지를 적용한다는 거잖아. 그 말 맞지?
백큐 레벨 존재가 원자에 떠나는 거예요.
그게 이런 수나
누가서
그래서 원래 방전 효과 설명이 있어야 되는데.
그러니까 난 그걸 듣고 싶은데 왜 그 얘기가 전에 아까
방전 효과가 없어가지고.
일단 보지 뭐. You guys understand what I'm measuring? They don't understand. We understand. We understand what you're talking about. They don't understand. Can you?
If you don't understand, then you should discuss, because here are many people.
Oh no, this is a seminar. Can you just explain what this equation? What are we measuring from here?
Here this equation measure this one EB, that means the binding energy. The binding energy
that is equal to
H nu minus EK. EK, that means the kinetic energy.
Can I?
Go ahead.
Actually, from here, using this experiment, we calculate this binding energy for any surface electron, how it's ejected. When we incident this energy, then as we know, the photoelectron emission, due to this incident energy, there is some energy need to be eject this electron. This is called the binding energy. How much amount of energy among this, the total incident energy, is needed for the eject this energy. This energy we will calculate, and after that, the excess energy, the surplus energy, will give that electron to kinetic energy.
And there is
that kinetic energy will detect the detector.
Yeah, that's what we are measuring. The kinetic energy.
That kinetic
Not the binding energy.
And regarding this one and using this equation, then we can get this binding energy.
H nu is total of.
Yes, it's already from our instrument. It's already known. Because when instrument incident ray.
Subtracting from H nu and.
Yeah, we know H nu because instrument give this incident energy.
Two parameters. One is H nu, that is none. We apply. Kinetic energy we measure by detector. By calculating this two, we measure by the binding energy.
Okay.
And we don't measure binding energy directly by calculating this two parameters.
From the equation, we can calculate. And basic requirement of XPS measurement, the basic requirement for a photo emission experiment are: number a source of fixed energy radiation, and then an electron energy analyzer, and then high vacuum equipment. It means these machines when we apply then high vacuum, that means ultra high vacuum is very important. So these machines, the basic X-ray source, sample, and then this one the electron energy analyzer or detector. And this part shows that the UHV, that means the ultra high vacuum. Without this vacuum, it cannot measure the surface. And this is the instrumentations of XPS. In this case, X-ray source, and there are several types of X-ray source, and then the X-ray beam energy normally 10 to 15 kV, and filament current 5 to 30 mA, and source powder, for example, source powder, X-ray flux, beam energy, filament current, like this. This means this is the simple or the very common tools, instruments for the XPS. But if we go to the XPS room, we see there's various type of instruments is there. The photoelectric process, in this case the incident X-ray. Look at here, this is the first we see this one. This is the incident X-ray, and this one is the ejected photoelectron. In this case, look at here, this is the valence band, conduction band, and topmost here, this is the feed electron level, and this is the Fermi level, and this is the 1s, 2s, 2p, like this. So in this case, XPS spectral lines are identified by the shell from which the electron was ejected, for example 1s, 2s, 2p. And another case is that the ejected photoelectron has kinetic energy. Already we discussed this kinetic energy we can measure from the detector, and we can calculate the kinetic energy equal to h nu minus Be minus phi. This is the all we know. If we know all this right side, then we can know the kinetic energy.
What is this pi?
Phi work function.
What is work function?
Work function, this is the constant value. We know from the maintenance, this is known, and this is a specific materials, this is known.
What do you mean?
I mean this is a work
What's
function
different
is
with-
constant value.
What?
Constant value. Work function.
No,
But-
work function depends on what kind of atom I'm using, what kind of material is using,
Yeah.
and what work function is.
Work function is, this is known, that means the constant value.
Yeah, of course it is constant value, but you change the atom, then the work function varies as well.
Yeah.
What is work function? That's what I'm asking.
Work function, I mean that this is the constant value, and we know, we know this is the known.
그럼 이함수가 아니라 뭐 지금 좀 이해가 되는데 저기 맨 위에 보이는 프리 일렉트론 레벨이라는 게 아까 말했던 베큐um 레벨 말하는 거고요.
맞아.
또 페리미 레벨이랑 저 베큐um 레벨 사이의 값을 뭐그 펑션.
그 예를 들어서 그 금속이 이온화가 되려면 이온화 에너지나 이런 것들이 필요하잖아. 그래서 그것들은 원자에 따라서 달라지잖아. 그러니까 그런 것들에 대한 것들을 우리가 이제 워크 펑션이라고 반영을 하잖아. 그리고 그걸
So can I say that work function actually it depends on material. Each material have different work function, but in case of the core electrons, say there, when the beam is incident, then from here to the just solid surface up to go to this surface, there is some work done. For taking from this core to surface, every material has individual that type of works need to this electron to the surface. This energy, corresponding energy called work function.
Not to the surface.
From Fermi level to, I think
Every atom has a different ionization energy
Yes.
from to remove to take out the electron.
Yes.
And that is so. Yeah, of course it's a constant, but if you change the atom, then it will vary.
It is atom to atom. This one can vary.
So
And this is known.
So I'm asking, what is the work function? Okay, that's fine. What is the Ozo electron?
OG electron. Look at here. The electron. This is a conduction band and this is a valence band. And the first one, when the incident X-ray attacks the surface of the materials, then the ejected photoelectron, this is ejected photoelectron, so this makes a gap, and this gap is filled up by another electron. At the same time, this one is rearranged and the immediate OG electron. So N electron falls to fill core level, balancing the first step, and then KLN OG electron immediate to conserve energy released in step 1. And this one we can the kinetic energy of the immediate OG electron we can calculate by the equation like this. The K EK, that means from the level, I mean that K equal to EK minus EL2 minus EL3. So OG electron, when we take the XPS, then OG electron energy we see, but this one we cannot consider. Just the figure shows the OG electron, but this one we cannot consider for the analysis.
hold on. 이게 맞는 얘기인지 지금 얘가 하는데 얘 우리가 얘를 can you go back? 지금 맨 안에 있는 코어 일렉트론을 때려가지고 그 빈자리를 얘가 채워주는 고 에너지인데 그건 맞지, 그건 맞는데 고기에서 나오는 에너지를 우리가 읽잖아. 근데 지금 그거는 뭐
그거 제 말대로 그렇게 쓰지는 않았습니다.
오제 일렉트론을 쓰지는 않는다.
예, 쓰지는 않고.
그럼 그게 그래프들에서 흔적으로 나오잖아.
그러니까 그게 이제 다른 원소를 측정할 때 오히려 그거 이 원소가에 기인하는 뭐 무슨 오비탈이라는 거를 이제 확정지을 수 있게 도와주긴 하는데.
그러니까 그 트레이스를 우리가 보잖아.
네, 그렇긴 하는데 그거를 이제 직접적인 이제 정량 분석 같은 데 사용하진 않습니다.
정량은 못해. 근데 정성을 할 수 있는 애톰에 따라서.
그냥 이걸 이제 이 여기서 나온 SP 픽잉하고 그런 게 뭐 SP를 확실히 해줄 수 있는 약간의 보완하는 에비던스 같은 역할을 쓰긴 하는데 그렇게 많이 쓰진 않습니다.
그리고 지금 이게 다시 돌아오면 이게 지금 얘가 이걸 때려서 맨날 코어 일렉트론을 때려가지고 지금 이케이션에서 보면 키네틱 에너지를 바인딩 에너지가 지금 어디서 어디까지 얘기하는 거지?
바인딩이 이제 저 플레일렉트론 레벨까지가 바인딩 에너지.
여기가 지금 우리가 때린 에너지에서 여기 에너지, 그러니까 프리까지 되는데 묶여 있는 데까지 해서
그걸 빼고 이제 거기에 작용하는 이런수의 값을 고정을 해주면 이제 날아가는 전체의 키네틱 에너지.
그러니까 거기서 말하는 이함수라는 것은 그러면
그 원소에서 이제 빠져나갈 때 필요한 측정값들을 뭐
그게 여기에서 그럼 어디에서 커트나 되는 거예요?
그게 그냥 인력에 의한
바인딩 에너지하고 이온 에너지하고 어떻게 되는 거예요? 일렉트론하고 저기 이온
근데 이온화 에너지는 주변에서 에너지의 순환이 있지 않습니까? 주변 계에서. 근데 이거는 이제 주변 계에서의 에너지 작용이 없고 단순히 그냥 파장을 집어넣어주는데 전자가 튀어나오면서 손실이 생기는 거고, 이온화 에너지 같은 경우에는 주변에 용매나 뭐 그런 애들한테서 그 오픈계 같이 연력하게 작용하니까 그냥 주변의 에너지가 바뀌고 그러는
근데
거지.
그걸 왜 여기서 고정을 했거든요?
왜냐면 저게 고정이 안 되면은 이제 저희가 보기에는 뭐 EV로 보니까 픽이 되게 뭐 세분화되어 있는 것 같이 나오는데, 만약에 원소마다 이람수가 차이가 좀 크거나 작게 되면은 정확히 구별이 안 되지 않습니까? 그런 거랑, 근데 이게 다 그 시스템 상에서 어느 위치에 나오는 거를 보정을 해줘서 보여줘가지고 저 정확히는 제가 따로 뭐 해보진 않았어요.
So we are measuring this kinetic energy from this equation. So this is the incident energy that we apply from the X-ray, and the binding energy. So the instant X-ray energy will attack the core energy, and then through this and then the electron eventually will be ejected, and this is the binding energy. So if you take out the energy, incident energy, the binding energy from the incident energy, that will give a kinetic energy, but there is a work function variation.
It's dependent on
Depending on the
material.
energy.
So in different material we use different X-ray.
No, X-ray is fixed,
Same.
but the kinetic energy that the detector is monitoring is the difference. So
Yeah.
we applied, as long as you use the same source of your X-ray, the HANU, the instant energy is the same.
Yeah.
But eventually the kinetic energy your detector will be measuring will be different. But there is from this equation, there is a work function value, but I cannot exactly explain but different matter, different atom has a different work function. So we kind of have to calibrate that kind of thing. But I cannot fully explain why we have to calibrate this work function. And next slide, this Ozo electron is very important because when you take the XPS, you will see many tail. So in the XPS spectrum, you will see many tail. And why this tail is coming? Because of this Ozo electron. Even though the X-ray incident hit the core electron, this Ozo electron, so you feel if you hit this core electron, it will kick out. It will generate vacant site. So the electron from the higher level will fill up. So it will keep happening. So understood? So, but that will give a different kinetic energy. For that reason, it will give some tail. But what Abu just said is but that tail is not that much important. We don't do quantitative analysis, but that kind of tail, the whole spectrum, the shape is quite important because that gives different the information about the different like atom or whether it's ammonium, whether it's amine, or it's sp3 or that kind of information. The overall shape, we can get the information about that. But from this tail, Ozo electron, we don't get quantitative information. Understood?
Yes.
Okay, go ahead.
This is a X-ray photoelectron spectroscopy machine, and this is a photoelectron spectroscopy meter. In this case, what type of instrument is here? Look at here. This is a X-ray source sample, and this is the computer system. That means analyzer control and various type of instruments. I mean that this is inside the machine. So I don't discuss about it. Just show this one, and I want to discuss about the application of X-ray photoelectron spectroscopy. First of all, quantification of the elemental concentration. For example, a Sample with unknown composition. Step 1. Aqueous survey scan to check what elements are present in the sample. That means this is the survey data. This survey data shows that oxygen, nitrogen, carbon, silicon, and number 2, acquire details of each element and calculate the peak area. Peak area, this right side top one, this is the nitrogen N1S, that's nitrogen. This area is 457, and the left below one, this is the silica Si2P. This is the area. This is carbon 1S. This is the area, and oxygen 1S. This is the area. It means that the details of each elements can be calculated.
How do you know which electron ejected? 1s, 2p. How do you differentiate?
If scan, this is the first the machine scan. If you want to scan the 1s, no, I mean the other 2s, 2p, then maybe, as I heard that, but I don't know exactly, we have to scan more.
Because there is like an NMR. NMR, like depending on your structure or like each chemical shift is already. But of course, it will vary depending on the environment. But the same way, there is some kind of
양성적 때문에 떨어져 나간 에너지가 달라서.
아니 그러니까 얘 말은 그게 아니라 그건 당연히 그런데 그러니까 내가 1S1에서 나온 건지 S1에서 나온 S에서 나온 건지
그거는 오비탈 간의 에너지가 다르잖아요.
그러니까 그게 좀 내 말에 정해져 있잖아. 그래서 그거는 우리 NMR 케미컬 시프트에서처럼 그 뭐라 그러니까 저 비교 차트라고 하나 코릴레이션 차트가 있지. So like NMR, like the arithmetic reason is usually set to A. So because that energy level for the 1s, 2s, depending on the atom, the energy is already determined known, right? It's determined, right? So the energy, that energy we are measuring, right? So like correlations chart, we can tell. Because in the literature, if it's the same atom, like one S or P orbital, so that will be given. So based on that, we can compare what kind of atom is present in your structure.
That means in the relation of the energy. This is the energy. How much energy is released? It depends on the energy. Detection of energy. You mean the computer detect the energy? How can we know this is the 1s or 2s or 3s?
Yeah.
So it means that the computer detects the energy, and from the energy we can know this is the 1s. That means energy is fixed.
The energy for
1s, this is a specific energy for 1s.
Per atom, depending on the
Depending on the atom, and energy also fixed.
Yeah, whether it's from the 1s or 2s or 2p, that is already has a certain.
We know, yeah.
Yeah, understood? Okay, go ahead.
And step 3, to calculate the concentration, look at here. In this case, we know that the element carbon, oxygen, nitrogen, silica, this is the area, and this more important things that we know the atom percent. And sometimes
이 EV 값도 같지만 너비도 같은 원자라면 같은 거랑 같잖아.
그거는 이제 그 안에 있는 거를 쪼갰을 때.
그렇지, 당연히.
예, 그거 안에 있는 걸 쪼갤 때 이제 파프위드스 맥시멈 맥시멈 뭐지? 파이트나. 그거를 맞추는 거는 그 안에 이제 막 본딩 같은 걸 맞출 때 맞추는 거고요. 그게 원자가 달라지면은 그거는 이제 이렇게 보여주는 픽을 맞추는 게 아니고 그 안에 쪼갤 때만 맞추는 거예요.
So we are just discussing about not only the X value, the EV. From the EV we can tell which electron is, whether it's an 1s or 1s or 2p or whatever. But also we can get some information about this peak width. We can also get information from this peak width as well. But that is more difficult because many atoms is overlap. So I think that's what Sang-Hyun has before he left. He gave excellent seminar on that, how to separate. We have to separate.
Yes, deconvolution.
Deconvolution. So there is anybody who has to handle the XPS, they have to be careful. 그래서 그거를 그 컨볼루션, 디컨볼루션이라는 뭐라 그러지? 그걸 프로그램에서 우리가 세퍼레이션 시킨 다음에
그게 이제 그 정확한 그 화학 조성에서의 나타나는 픽의 일렉트론 볼트 에너지는 이 문헌들에서 이제 첨부를 하고요. 거기 첨부된 위치에 맞춰서 픽들을 설정한 다음에 여기가 같게 나타나게 여기가 같게 분해하게 이제 프로그램에서 입력을 해서
우리가 분해를 한 다음에 프로그램에서 so
포지션을 잡아주고
we set the position and based on that program, using that program we separate the pick and 그다음에
그렇게 분해된 거로 이제 다시 그냥 분해된 걸로 이제 이 화학 조성이 양이 얼마나 있는지 알 수 있으니까
그 픽 위스에서부터 그걸 가지고
넓이랑 넓이로
면적
이게 그 분해된 픽들의 넓이로 상대
가지고 이거하고 이거 조성을 우리가 알 수 있다는 거지. So I think that was Sang-Hyun gave us excellent seminar on that. So 그 deconvolution에 관한 뭐라고 하지? 그걸 하는 거를? We don't know the term, but when you get the X-ray spectrum, that we have to do. We forgot that term. Deconvolution, I don't know. But we have that software. So using that software, you kind of have to separate because using the different atom has a different, so it may overlap. So after that separating, then it will separate. Then from the overall width, you can tell whether, because then we separated, but that's very important. So after separating, then we can tell the ratio between two elements. So based on that, we can tell even how much the function has been introduced to us, so how much conversion of your reaction has been done. 근데 이번 상현이 문제가 됐던 게 그
와이너비를 안 맞춰. 하프 위드스 맥시멈 하이트를 안 맞춰도 그것 때문에 이제 그게 들어와서 이제 그거 수정.
그건 네가 나가기 전에 한 번 더 세미나 해주면 좋겠네. 상현이 거.
저도 한번 다시 해볼게요.
Okay, go ahead. I just asked Bukju how to use that program, and Sang-Hyun at his JPS paper, I think we got a very strong comment from the reviewer about that thing. So I asked Bukju to give a seminar on this one. Okay, go ahead.
And this is the XPS analysis of pigment from Mami at work. The Egyptians, Mami second century AD, World Heritage Museum, University of Illinois. In this figure, this is the survey data. XPS analysis shows that the pigment used on the Mami wrapping. This shows that the lead oxide rather than iron oxide. And look at here, this is the deconvolution. I mean that if we try to know this compound, what type of compound is it? This means this is a lead, and this lead shows the several type of peak. If we do this is the deconvolution, that means the high resolution. This high resolution shows the several type of peak. These two peaks shows that the lead oxide, lead 3O4, and this one lead dioxide. That means this is also contained with the lead 3O4. So actually in this case two type of lead compound are here. This one if we draw the high resolution, but if we consider the survey data, then we cannot confirm the what type of lead contained here. Just we can know that means the lead, chlorine, sodium, carbon, calcium, nitrogen, oxygen, this compound contains.
Okay, go ahead.
And next figure, this one, XPS analysis identifies the functional group present on composite surface, chemical nature of fiber, polymer. It means that if we look at here, this is the survey data, and this part, if we draw the high resolution, then we know the what type of element is here. Very similarly, we know the functional group if we draw the high resolution. Then look at here, in this case the carbon oxygen double bond, carbon oxygen just single bond, carbon carbon bond. So if we draw the high resolution, then we can know what type of functional group inside the compound.
이거 얘기하는 거잖아, 혹시야?
예.
저걸 가지고. So this is what I just talked about. So if you take the XPS, you won't get these separated. So overall, it will just look like this one. So you don't know then whether this is the C or O or this even the SP. This the P orbital. So from this XPS, then you have to deconvert or whatever that you have to separate this one. Then after separate, this is after separation. So then from this peak you can separate using that program. So there is some important information. So after separating this one, then you will have this over the integral below this peak. Then from here you can tell how much carbon and how much CO and how much CC is in that your molecule. Understood?
After draw this peak, the software shows the percentage of the carbon oxygen double bond, the area. We can find from the calculation. And this slide shows the chemical shift due to the electronegativity effects. So in this case, this is a functional group. Already I said to you that we can confirm the functional group after taking the XPS. So look at here, this is left side, this is the functional group, hydrocarbon, amine, alcohol, like this. And the right side, this is the binding energy. So a specific functional group, in the respect of a specific functional group, we know that the binding energy is fixed. But this binding energy sometimes it can sense a little bit if this one bind with another negative metal or something like that. I will discuss it later. So in this case, look at here. If it show that the atoms of the higher positive oxidation state exhibit a higher binding energy. Look at here. This is carbon, nitrogen, oxygen, Cl, F, like this. In this case, due to the extra coulombic interaction between the photoemitted electron and the ion core, this ability to discriminate between different oxidation state and chemical environment, it means look at here, this is the electronegativity increases like this and the binding energy also increases. So in this case, this is carbon hydrogen, carbon carbon, binding energy is 285, carbon nitrogen binding energy is 286, and carbon oxygen binding energy is 286.5. So like this is the electronegativity increase, binding energy increase.
So you're applying the same energy binding energy, as you see, is different depending on the functional groups. Over the kinetic energy that you see will be different. So you will see a different expert, which is E3.
And this figure shows that the left one shows that the XPS spectrum of N1s core level. In this case, the amine peak N is to NO2 and NO3. This is the specific. This we can, if we draw the high resolution spectrum, then this one can be separated. But if we try to know from the survey data cannot show this one. That only deconvolution or the high resolution can show this one. The right side figure shows that the XPS spectra of silica 2P in nanosize silica particle 0.5 eV shift induced by the addition of BA. It means that, look at here, the top this one silica SiO2, but this one, the below one, silica with BA. So it means that when BA attached with SiO2, then the chemical shift is a little bit different, but that means this one is shifted 0.5 eV. So this is the effect of beryllium BA.
국주야, 그러면 이게 테일은 뒤에 나오는 테일들은 저 아까 디볼루션인지 그거 할 때 그럼 테일들은 어떻게 저 인덱스가 높지 않기 때문에 무시하는 거야?
그 베이스 라인을 잡을 때 그러니까 이게 어차피 해보시면 다 해보면 알겠지만 저 메인 픽을 중심으로
당연히 잡는데
좌우를 좀 벗어나면은 더 이상 분해가 안 되거든요. 그래서 보통은 그 XPS 그래프가 이렇게 사선으로 나오기 때문에 테일이 있는 것처럼 잘 보이는데, 그래서 이걸 베이스 라인을 잡을 때 약간 이렇게 올리면서 또 이렇게 이거 무슨 그래프라고 그러죠? 사인 그래프라고 그러죠? 이렇게 곡선으로 베이스 라인을 잡게 된다고요.
그거 좀 테크닉을 좀 가르쳐 줘야 되겠다 다음번에.
자꾸 해주잖아.
We are just discussing. So as we discussed today, so you take the XPS, then not we are. He's talking about only the main peak, but we have seen that there will be some other tails as well. So when you observe the peak, whether there will be some tail as well, which although the intensity are not very strong, so how can we ignore this tail, because we only have to focus on the main atom peak, right?
Yes.
So Gokju just said that I think Sang-hyun is going here. So Sang-hyun was expert in Nawa, but Gokju has done most. So I just asked him how to do from the menu, from the program, how to eliminate that small tail peak. From after I don't know when Gokju's turn is coming for the XPS. I think it's quite important to know. Okay, go ahead.
Yeah, this is some real data. This is the real data of the publication paper. In this case, this research group, they synthesize the amine compound from the azide. That means azide group sends to amine group, and this structure, that means the final compound structure and the starting material structure, that means composition, are similar. Each can they discuss each contain same, because the survey data, this topmost left one is the azide compound and the right side one is the amine compound, and both of these compound survey data shows that the zinc peak, oxygen, nitrogen, carbon, here also similar, only intensity a little bit difference, but the position and the element are same. And figure below figure shows that the azide contain compound for the nitrogen N1 peak. There are two types of peak. This is the high resolution peak. High resolution peak, in this case, this is the nitrogen. This nitrogen, very small peak. if we draw this small peak, that means deconvolution, then this shows that two peak, very big peak, two peak. One is the 400 and another one is 401. This 400 and 401 is a azide group contained peak because they give the reference, another paper reference. They shows that if the compound, if the azide functional group in your compound contain, then this deconvolution peak should be 400 and 401. So they prove that this nitrogen is azide, and another nitrogen, that means look at here, there also another nitrogen. If we draw this nitrogen with a deconvolution peak, that means high resolution, this high resolution shows two peaks, and one peak is 399 and another peak is 398. So, and another case is that the peak shape and intensity is different, but more important thing is that they shows that the amine is 399 and 398. They have the they give the reference. So if we try to write a paper, then our peak should be, we should give the reference. I mean that this amine is okay.
So based on this XPS data, you just want to say, is this your paper?
Yeah.
You just want to say that the azide peak has been fully converted, reduced to the amine. Is that right?
Yeah.
But what if the azide peak has not been fully reduced? There are some. If there is a azide, how the XPS is going to look like? How can you tell them? Because they are very close, right?
Yeah, very close, but this peak is fully different. Actually, this upper peak, that means the survey data shows the nitrogen, both of the survey data contain nitrogen, but this nitrogen peak is different. If we draw,
I know. 그거 어떻게 하는지 그러면 그거 만약에 이게 100% 컨버전이 안 갔으면은
이게 원래는 그러니까 저게 지금 제가 오른쪽 거는 NC랑 NH도만 나눠놓고 왼쪽 거는 NC랑 N만 나누는 거거든요. 제가 봤을 때
이게
왼쪽에 NC고
NC,
오른쪽에
this is NC, this is
NH가
NH.
왼쪽에는 그게 NC고
NC,
오른쪽에 NN 같은데 아저이게
N nitrogen.
원래는 저렇게 두 개만 하는 게 아니라 저 네 개의 픽을 다 어사인을 해야 되거든요. 그 서로의 두 그래프에 둘 다. 그러니까
같이
왼쪽에 있는 것도 399랑 398에 대한 에너지를 이제 포함을 해서 그려야 되는데 이게 저 그래프만 봐서는 완전히 픽이 원래 399, 398에서 나오는 픽이 왼쪽에서는 이제 거의 없어졌으니까
없애고
400이랑 401만 한 것 같은데
그 100% 같다는 거.
이게 XPS는 항상 자기가 보정을 해줘야 돼요. XPS는 항상 자기가 보정을 한 번 더 해줘야 돼요. 그러니까 기준을 어떻게 세우냐면은 CC 본딩으로 세우는데 CC 본딩이 298에서 나온단 말이야. 298나 278나 어쨌든 CC 본딩에 나오는 기준이 정해져 있어. 그래서 이게 측정값마다 CC 본딩에 나오는 EV 픽이 위치가 조금씩 다른. 그래서 모든 측정값을 만약에 얘에서 C가 299가 나오고 얘에서 C가 298이 나왔으면 얘를 마이너스 모든 픽의 모든 일렉트론 볼트를 마이너스 1에서 298을 맞춰줘야 되는데 이 작업을 하면서 위치가 뭐 바뀌거나 그래서 안 나오거나 CC 보정
그거는 당연히 했다고.
예, 그거는 이제 자기
보정을 해주는
건데
그다음에
그러니까 보정을 해주고 그렇게 CC 보정을
그럼 이 정도 차이에서 만약 보정 안 해줬으면
그러니까 이게 보정을 해준 값인지 안 해준 값인지 제가 모르겠는데 사실
그래도 했다고 믿고
완전히 홀전돼서
근데 N 값이 저렇게 스무스하게 나온다는 게
그리고 인쇄시 때 보시면 다른 게뭐 카본이 뭐 9만까지 인쇄시티 나오는데 아래쪽에 질소가 인쇄시티가 3,000 정도지 않습니까? 이게 원래는 점으로 찍혀 있으면 되게 지저분한 상태였을 텐데 이게 원래 그래서 XPS 그래프를 그릴 때 점 위에다가 선을 이렇게 그리거든요. 그래서 이게 진짜 지저분한 상태면 거의 알아보기 힘들 정도라서.
아니 그러니까 얘 데이터에 대한 신뢰도를 우리가 얘기하고 싶지는 않고 그냥 이거 데이터 믿고 내가 궁금한 거는 보정했다고 치고 보정을 했는데 두 개가 만약에 100% this is a 100% conversion, but what if this is not 100% conversion? Then how do we know whether how much it'll be because they are very close?
쪼개는 걸 그냥 다 모든 픽에다 적용해주세요. 쟤는 지금 2개씩밖에 안 해놨는데 전후에 픽에
그냥 겹쳐 있을 거 아니야?
겹쳐 있어도 해야 돼요.
아 그걸 어떻게 해?
그건 기계가 알아서 나오죠. 그게 합쳤을 때 저 그래프의 모양이 나오는 거였으니까. 그러니까 커다란 그 서페이스에 있는 그래프는 디바이딩 된 애들이 다 에디션 돼가지고 나오는 그래프여서 그 포지션을 딱 잡아주면은, 그러니까 포지션을 잡아줬을 때 뭐 이렇게 만약에 지금 저게 400이랑 뭐 399.5 정도라고 생각을 하면은 그 포지션을 잡고 여기 위치에서 디바이딩을 하라고 하면은 395는 399.5는 이만큼만 올라가고 얘가 이렇게 대부분을 차지하는 그래프가 알아서 그려질 거예요.
아 그래?
예.
그럼 그걸 세퍼레이션 심지어 할 수도 있는 거야?
이게 서프레이션이 자동으로 꼭 그래서 이렇게 돼요. 그래서 저렇게 그 셀같이 끌리는 부분에서는 아무리 걸어봤자 배를 합쳐보는 이 그래프가 나올 수 없어서
1대1이면
1대1이면은 원래 이게 이렇게 있고 그냥 나가고.
Can you explain in English? Is that possible?
그러니까 만약에 this surface, the bigger graph is the small graphs are adding
Inside.
shape. So when you're think about the DC and CH, CC로는 1대1이 안 되죠.
CO
What? Something. And if we contain the A and B value in the same ratio, the 1 to 2, the dividing graph will appear like this. So if when you do this act, so you should be doing the CA position and CAB position and set your position and calculating to calculating to software. It can 알아서 automatically divide this peak. So think about when the A peak is located here and B peak is located here, and you do the calculate, the dividing peak appear like this. Understand? The dividing peak appear like this.
만약에 1대1이 아니라면
Yeah.
if this is not 1-to-1 ratio, then you have some different as he just drew.
1대1이 아니면은 if the CA and CB content is not 1-to-1 ratio or something, is this position do not located on here. Yeah.
It will change its position.
Yeah. It is automatically located here. So when you do calculate, you can estimate this area and you can compare with this ratio.
국주야, 내가 마지막 내가 잠깐 놓쳤다. 만약 1대1이 아니라면
1대1이 아니면은 이 점들이 이 안에 두 개가 위치가 안 됩니다. 왜냐면 이 점들의 위치는 이 에너지에 대해서 포인팅을 한 건데 이 에너지가 그럴 때 이 얘네들이 1대1이 아니면은 무조건 에너지가 많은 쪽이 픽이 커지게 나올 거기 때문에 이 에너지가 적은 쪽에 어딘가를 약간 벗어나는 점이 찍힐 거고 그걸 상대적으로 많은 애가 그 안에 들어가는 점을 찍힐 거고 그래서 일단 포인트를 잡고 계산을 하면은 알아서 이게 디바이딩 되기 때문에
그러면 NMR에서 우리가 인테그랄에서 10% 에러를 무시하는 것처럼 XPS에서 저 아까 네가 고정선을 잡는 그걸 죽여버리는 정도는 어느 정도가 더 보는 거야?
그거는 제가 저기까지 정확히 모르겠는데 XPS도 어느 정도 그 에러 범위는 있는 걸로 알고 있거든요. 그래서 그냥 절대적 비교는 안 하고 상대적 비교.
근데 지금 그거 말하는 전제 조건에는 아까 네가 말한 것처럼 그러면 절대적으로 얘하고 얘를 고정선을 잡아서 정확하게 그게 고정선
그거는 이제 CC로만 하고
그걸 해줬다는 전제를 깔아야 되겠네. 안 그러면
예, 그러면은 아예 분석이 안 되고 그래서 원래는 제 생각엔 이걸 분석할 때는 여기서는 이미 뭐 포인트가 벗어나서 안 집어넣어도 괜찮은 것 같은데 만약에 for example this area is located on here you should be assigned this peak also. Okay? Now this peak is outside of this range so this peak is do not denoted but if you are this graph located over here for comparing the conversion ratio, you should be this peak also assigned to the peak. Okay. 그래서 지금은 벗어났기 때문에 상관없는데 들어가 있을 때 같이 해서 비교를 하는 게 맞을 것 같아요.
저기 같은 그래프가 다른 그래프를 간다고
그게 아까 말했던 단치폭 잘못 설정하면 그렇게 나와서 세면이 형이 리셋한 그 한번 봤던 게
네. 그래서 그거를 맞춰주려고 리너비를 맞추면은 이게 네가 바꾸고 싶어도 안 바뀌어.
Yeah, I think I understand. So I think that that's very important information that we had the trouble for Sang-hyun's paper. So, Kukju, can you prepare a seminar for this one, including how to use that program? And so you see that other than this nitrogen, all these other functions will be the same. So he's just focusing on this nitrogen. I think this is your last page, right?
Yeah.
And usually the
No, the last place. I have a.
You have some our paper as well. Our group paper.
No, I just include my.
Usually the people usually include our paper so that everybody. Okay, go ahead.
And another one, very similar paper, but there is a good information. In this case, after functional analysis on the amine, we incorporated copper chloride. So in this case, the copper chloride, I mean that this left side number D is the N1S peak for compound 2, that means the middle compound 2, and this another one, this one for compound 3. Compound 3 all are nitrogen N1. I mean that there is a nitrogen, this is amine, this one also amine, but this amine a little bit sense if when I insert the copper chloride. I mean that the copper chloride insert, then the nitrogen shows only one peak and the peak position is 400, and in this case the amine position 399 and 398, a little bit difference with the before one. It means that almost 390 and this one is amine peak. Already we give reference, many paper reference, and this one a little bit shifted because we inserted copper chloride. And another information is this is the inset. This inset shows the copper chlorine S1 peak. So chlorine S1 peak, it means there is a chlorine, but here we shows that there is no chlorine peak, but there is a chlorine peak. And very important information we can discuss from this peak, that means right side peak. Each peak shows that the copper 2p 3/2 and copper 2p 1/2. This is the orbital splitting. So in this case, the copper type of peak, copper 2p 3/2, and this one, its mean this is the copper chloride. That means copper 2, not copper 1. I mean that the more important thing is that this figure shows the satellite peak. This satellite peak is very special for the copper 2. If there is no satellite peak, it means this is the copper 1. I mean that after modification, after insert the copper chloride, this copper chloride is copper 2 or copper 1. Because sometimes the reviewer asked, your copper is copper 1 or copper 2. We think that this is copper 2 because it contains the satellite peak.
Hold on. You added copper 2. And if the copper to chloride is binded to the morph amine,
Yeah.
then what kind of difference do you expect then?
This time, when this one copper fluoride bind with amine, this is the coordination, the metal and amine coordination. After coordination, then the primary amine, that means the left side figure is primary amine. This is the nitrogen 1s. This one also nitrogen 1s middle one. The nitrogen 1 is fully different after insert the copper chloride.
But you have not shown the nitrogen peak. You just showed the copper first of all.
First one, there is no copper. In this case, the survey data don't show the copper. I also show another.
No. You have a different nitrogen, and after coordination, this nitrogen also will be different. That's what you're trying to say, right?
Yeah.
But there's no nitrogen peak, first of all.
First one?
After coordination, you did not show any nitrogen peak.
After insert the copper, this middle one, the nitrogen peak of the.
This is after coordination?
Yeah.
Oh, not this as it?
The middle one, the.
Not this nitrogen, this is after coordination?
Yeah.
I see.
CL이 클로라이드라고 써있는데
어디?
이에 클로라이드에서
this
클로라이드
This number E, this one is 3, that means that this compound.
is chloride.
No, chloride is the insert, and look at here, this is the compound 3.
So this is the nitrogen peak of this coordinated one.
안에 조그맣게 들어간 게 클로라이드.
And 이게 chloride라고?
네네.
이거 나이트로젠이고.
예.
And what about the copper? Then you just saying that the copper is a copper chloride. Of course, you added copper too. And after coordination, how will the copper peak changes? From copper to that changes to copper 1? Or?
Yes. Sometimes if we insert the copper chloride, sometimes the copper 1 is formed as copper 1. Copper chloride can sense copper 1, but in this case, this is a copper chloride. That means this compound copper chloride is don't break. This just bind with amine, and this is the information because the satellite peak. This is satellite peak is very important for copper 2. The copper, if this one is copper 1, that means the satellite peak is detected.
I don't understand. You added copper 2 chloride, and why are you concerned about the copper 1?
If the copper is breakdown and then the oxidize, and I mean that the copper 2 can easily convert copper 1. Some paper they shows that after insert the copper chloride is convert copper 1.
And if it's converted to the copper 1, that will not bind to the morph?
Maybe bind, but the reagent, this is catalyst. The catalyst reagent will be sensed.
Oh, I see. So the copper still, this is chloride. So for this copper, there is still a vacant site, and through this vacant site, your copper nitrogen, your morph will be coordinated, right? So this coordination will not affect your copper, the oxidation state of your copper.
Yeah.
Right? 그러니까 이게 지금 카퍼 이가가 있고 카퍼 일가가 있는데, 그러니까 그 반응성을 가지려면 일가하고 이가하고 완전히 다르니까 이가가 유지되어 있다. 뭐 어떤 의미에서인지, 그러니까 이게 안 바뀌었다. 이게 코디네이션 된 이후에 나는 코디네이션 됐다는 걸 증명을 뭔가 하는 에비던스로 생각을 했더니 그건 아닌 것 같고, 그냥 어쨌든 바인딩 한 이후에 또 그 카퍼 이가가 여전히 카퍼 이가가 있다. 그냥 그 얘기를 하는 것 같네요. So how many pages do you have more?
Only maybe 1 or 2 pages.
Okay, so I think what he's trying to say is that so he has developed this morph with amine with the catalyst. So this through this amine and the copper, the copper has a lot of vacant sites. So through that bacon site, the nitrogen can coordinate to this copper. But I expected that this XPS will give evidence for the binding between this morph, the amine of the morph with the copper, but that is not the case. But that as evidence, he just showed use this XPS nitrogen thing. But what he was trying to say is that the copper 2 chloride for some reason can be changed. The oxidation state of copper 2 can be changed to the copper 1. But then the reactivity of the copper 1 is not as reactive as copper 2. So he just wanted to show that the oxidation state of copper 2 has been retained even after the coordination. So the reactivity is still active. The activity is still, that's what he's trying to say. Okay.
And next slide, this one shows that in this
what kind of evidence that are you using to support? Can you go back? What kind of evidence then are you using that your copper has been coordinated with your morph?
What type of? In this case, I mentioned the XPS and then XR.
You mean this nitrogen pair?
질소로 보면 될것 같아요.
그 앞에 게 이미 저 아자이소피가 아니라 아민 그게 나온
그 아민이 이렇게 변했다는
네네.
거 가지고 코디네이션이 됐다.
코디네이션 되면은 아무래도 전자를 끌어갈 거니까 에너지 좀 증가한다.
그래서
근데 다른 게 너무
근데 그걸로 충분하지 않을 것 같은데.
너무 다른 애들이 없어서.
What kind of are you using for this coordination? You're probably using ethanol, right?
Solvent
So-
and ethanol.
And you remove the ethanol.
Yeah. After finish the reaction, remove the ethanol, dry, and then use.
근데 카포에 에탄올도 그럼 우리가 나이트로젠을 보니까 그건 상관이 없는데. So I'm just curious. I understand. So this is the amine peak of the reduced one, and after coordination, this nitrogen peak has fully changed. So that it has binded the nitrogen has been coordinated to something, but still, as an organic chemist, it's not a full evidence that you have a coordination between. There is a coordination between your morph and copper. So other than XPS, I'm just curious. Is there any other evidence that?
Yeah. We give other evidence, for example, TGA and
TGA.
Yeah. TGA not very good, but we give this is one kind of.
TGA, what kind of? How do you?
TGA just we try to show, we try to demonstrate or try to give some information. So what is the difference after modification and the before modification? Because if the metal, the morph, this one also contains metal, this one also contains metal, but after the copper, then the TGA a little bit different.
You are seeing the degradation of what? Degradation of copper or degradation of the amine or what?
Yeah, degradation of the copper mainly because
Copper?
Yeah.
Copper degradation of
Metal.
the metal degrade. What temperature?
Metal not degrade after modification with the metal, then the.
So what kind of degradation are you looking from TCA?
Yeah, TGA, I see that the number 3 compound, this one, if we consider the white loss,
What weight loss or what?
white loss of the compound 2 and compound 1, 2, 3. Compound 1, compound 2, compound 3. The
So
white
which function? You mean the nitrogen peak, that the amine peak, the degradation of which peak? That's what I'm asking.
actually,
Amine.
no, overall, 100, we know that the 100, 150, maybe the whatever, something like that, but the below, the final about 800 or the 700, 730,
Which-
in this area,
Which is corresponding to what degradation?
the white ratio and the temperature.
That range, the weight loss is due to what? Degradation of what?
Like-
700.
Yeah, this is we do this 800, and this is the, for example, this is 750. Then in this case, a little bit like this. This 2 is almost similar, but 3. This is the white loss. This is the white loss. So in this case, this is the number 3, compound number 3, and this is the 1.
And I'm asking that is the due to what? That is due to what? Degradation or what?
We hope that this one after modification doesn't contain the metal copper, then the white loss, in this case this one white loss is a little bit less than this one.
It should be that
Weight loss should less if copper incorporated. And
no, I'm asking the weight loss is due to what? Due to the amine or more?
here it should amine reaction because when it will interact.
아민이 온도가 저렇게나 올라가나?
When it will interact with copper.
No, I'm asking.
그 제가 말하는 게 그거 같은데 뭐
700, 800, this is better.
바인딩이 있으니까 조금 더 올라갔다는 얘기잖아.
그거 말하는 게 아니라 그냥 다 날고 나가지고 저기 남은 게 푸가 더 들어가니까 뭐 남은 게 더 많다 그거 얘기하는 것 같은데.
그 지금 자체가 뭐가 분해된지 그걸 내가 물어보는 거잖아. So from the TGA, as you said, you have some degradation pattern, and the first pattern below 100 something, then we usually call this as a water ping and sodium ping. And the second reason, let's say ammonium degradation, and then some polymer alcohol degradation. We first assign, and then from this each assignment, then we can tell how much you have more ammonium. Then of course you will lose more ammonium, right? So I'm just asking, okay, I understand that after coordination, the overall weight has been increased. Okay, then I understand. But what is that due to? That degradation is the amine degradation that you are looking. That you just said that this last peg is slightly increased. But that is the amine or that is the copper or what? That's what I'm asking. That degradation is due to what degradation? You understand my question?
Yes, sir. Yes.
You understand my question?
Yeah.
And answer it.
Actually, the last part, the retention mass is the inorganic part. There is
Retention
no
mass
degradation.
should increase
Increase after incorporation of copper. And above that degradation may be due to this polymer chain degradation.
So thermally, your morph becomes more stable. That's what you want to say.
Yes.
So
And
you don't know what.
Finally,
Actually, we want to say the morph is stable with this temperature, and
No, I'm not.
final weight percentage should increase.
그러니까 그거잖아. 그러니까 이게 어떤 이유였는지 코디네이션 된 다음에 그게 이쪽으로 좀 안정됐다라는 건데. 그러니까 저 온도가 되면 700, 800도 가면 카본이 타지. 거기서는 이제 그래파이트나 이런 걸로 변해버리지. 근데 그 그래파이트나 카포가 들어가면 그래파이트가 무슨 얘기인지 모르겠는데 이게 왜 올라가는데 그런 건 이게 왜 올라가야 돼?
저게 제가 생각할 때는 그냥 끝에서 그냥 남아있는 레지두가 더 많다라고 말하고 싶은 것
근데
같은데
그 레지드라는 건 카본에서 나오는 레지드잖아.
카본은 700도 넘어가면 안 남아있습니다. 저거 그냥 다 컴플 겁니다. 금속이지 남아있는
아니 이게 금속이라고? 금속이라고?
네, 저거 750도 넘어갈 때까지 넣어서
같은 무게를 로딩했을 때 거꾸로 서 있는 것도 많잖아.
아니 그게 아니라 마지막 피까지 올라가는
올라간다. 거기 있을 때
올라가는 거는 산호 같은 걸로 설정할 수도 있어. 근데
아니 왜 얘만 위에 올라가는 거야?
그러니까 도리가 산화가 되는지에 대한 뭐 문헌이 있으면은 그 온도에서 도리가 산화가 일어난다라는 에비던스가
그게 카본 옥사이드가 돼서
네, 그것 때문에 무게가 증가한다고 주장을 할 수 있는데 그게 있는지는 잘 모르겠어요.
저게 저는 계속 처음부터 들 때부터 궁금한데 저게 그냥 믹스드 돼 있는 건지 코디네이션 돼 있는 건지
아니 그러니까 그 에비던스를 내가 TJ를 얘기를 하니까
TJ에서는 잘 모르고
So still we don't understand how come the TGA it cannot be an evidence that I ask you how we can tell that your morph has been successfully coordinated with your copper? So that TGA overall does not give any evidence for that, right? You agree?
Yeah, actually, we give several type of experimental data. For example, IR, XPS,
IR. Oh, I see. 저 탄소도 저 700, 한 5, 600 넘어가면 그거 저 뭐라 그러니 그 수처럼 돼버려가지고 쭉 가.
그러니까 저게 이제 산소 분위 계산이냐 이너트 분위 계산이냐 이너트 분위 계산이면 화분 분이 날아가고 무게가 나오고
이게 IR
산소 부분에
IR이나 그 카포의 무슨 트랜지션 뭐 저런 걸 쫓아가면 될 것 같긴 한데.
근데 애초에 CJ용은 2번하고 3번하고 비교를 못하잖아.
이쪽에 믹스된 거
올라가면 그 코디네이션 자체도 깨질 것 같은데.
그건 깨지겠죠.
그럼 그거 비교를 못하는 거 아니에요?
그러니까 저거는 단순히 컴포넌트에
and then we took the tail mapping, same mapping. So from the tail same, we know the metal, whose metal and another element. I mean that, and the mapping. We did the elemental mapping from the same.
텔레스 EDS 한번 할수 있겠네.
EDS 한번 볼 수 있겠네.
근데 이게
I think you can get some idea from the EDS. Okay, shall I go on?
Next one, this one, we synthesis compound 3. This is homogeneous, and this homogeneous compound we attached with the graphene oxide. So after graft this homogeneous compound, we use this one as a catalyst, and we analysis this one. For example, one analysis method we use the XPS. This XPS data, this one shows the XPS analysis of 4, that means the final compound N1S and B, C1S and C, this is O1S, and D, this is PD, palladium 3D. So this information support this compound functionalization or the grafting is okay, because look at here, this N1S, this one shows the NAs and the NAC. It means that this compound amine functionalization group is here, because we know that the graphene oxide there is no amine functional group. So this one shows the amine functional group. So this is one kind of evidence. And from the C1S,
hold on. Can you 이거 왜 이러지? I cannot see your compound too. What kind of functional group do you have over there?
This number 2 and 3 almost similar.
Without palladium, is that right?
Yeah, this is palladium
With the imine and the
yeah.
is that right? Is that two?
Yeah, O and the
Imine.
NAs, yeah, and this is the chloride.
So
That means palladium chloride is insert in this compound.
compound two. So the two is the imine and the ketone, right?
Yeah, ketones here.
이 아모늄은 어디서 나오는 거예요?
맨 처음에 HCl, HCl.
이거야? 이게 그럼
맨 처음에
이게
HCl, HCl.
And this XPS is the XPS data, the of what? Which one?
Number 4. Number 4, last final one.
A.
Nitrogen. N1S, nitrogen. Nitrogen, this is a high resolution, that means deconvolution data.
And where do you get the ammonium?
Ammonium, the salt pit. How do you
Ammonium
get
normally NH3 plus. Normally, if the ammonium compound SPS peak sometimes contains the NH3 plus like this.
Say it again. Say it again. What was it?
If we do the deconvolution or the high resolution, then we see that if amine group is there, the amine group sometimes change or the change to the NH3 plus, and it shows some peak. Almost we see this one.
You're saying that the ammonium peak usually is occurring for pretty much all the amine. Is that what you're saying?
If the compound contains amine, then XPS shows the NH3 plus.
그래? 그 얘기 아니잖아. 지금
How that amine get this proton?
얘가
If we don't treat this acid, then
하니까 아모늄
is it
나와.
possible?
This
그걸 보여주는 거 아니야?
surface contain the amine. If the compound contains amine, then
아니 출하는 지금 남아 있는
XPS peak normally shows this one.
M은 지금 아모늄 피크가 원래 따로 나와.
잘안 보여.
근데 무슨
근데
옛날
보내?
이게 출발 문제에서 이건 뭐야? 이건 다른 내용이지. 출발 문제에서 따라왔다는 거야? 아니면 얘가 코디네이션 된다면 이게 아모늄처럼 되니까 그게 보인다는 걸 얘기하나?
쟤는 그냥 하이레졸루션에서 나올 수 있다고 하고
하이 레졸루션이라는 건 뭘 얘기하는 거야? 우리가
정확히 저 XPS에서 말하는 하이 레졸루션은 저 일렉트로 바인딩 에너지 볼트를 좁게 찍는 거.
이걸 좁게 찍는 걸 얘기하는 거야. 이거 우선 그
대신
감도하고
어차피
상관이 없다고.
오는 빔은 똑같으니까. 근데 제가 정확히
We never observed any ammonium peak for the amine. We are using many amine compounds. But we never observed any ammonium peak.
몇번 찍어가지고.
I don't understand how you get this ammonium peak. And so from this XPS, what kind of information can you get?
First one we inform from here the number A. This is the NH peak, that means the just compound 4. Compound 4, that means that compound 3 is attached with graphene oxide. This evidence is NH peak is come from this XPS. And number B shows that carbon nitrogen, this is the C1S, number B C1S, and C1S shows that carbon nitrogen peak. The carbon nitrogen peak, so this is one kind of information, because we know that graphene oxide there is no carbon nitrogen. And number C shows that the carbon oxygen and this is the oxygen O1S, in this case C double bond O. But this one is very difficult to say about the information because the graphene oxide and this compound also contain the CO group. But we just say this is maybe this one or this one. But the good information is that the number D, this is the palladium 3D. Palladium 3D, this is the orbital splitting. In this case, the palladium 3D 3/2 and 5/2. First one 343.13 eV and 333.60 eV. This is the palladium 2. If this compound peak is 335 and 341, then that means that the palladium 0. So while we insert this type of palladium complex, if this one is broken, it don't maintain the structure, similar structure, then this peak should be different. So this information shows that the graphene oxide contains palladium, and this palladium is a palladium 2 because this is the value.
Okay, I understand. But what if, okay, so you have a pretty much all the peak for pretty much all the functional group of all the atom. But how do you know that whether you have only a mixture? What if you have only palladium? If you mix only palladium?
If the mixture, for example, I did many experiments similar. If the mixture of palladium 0 and palladium
No,
2,
not the palladium 0 or not. Even though there is no coordination.
if no coordination, because after preparation this one I washed with the fresh solvent several times.
But that is not the answer that I want to hear. But still, you have all the peak. I understand you have all the peak for all the palladium and all this CO or whatever. But still, there is no evidence that you have a coordination between your MO, this LGO functionalized amine with your palladium from this XPS, isn't it? Do you have any evidence that there is a coordination?
Actually, there are several types of reference because this is the pyrene moiety. Do you know this is a pyrene moiety, and this pyrene moiety this can bind with graphene oxide, the pi-phi interaction. This is several types of paper than evidence.
No. That's not what I want to hear. If there is no coordination, you will have an imine peak, right?
If there is no coordination, then it is impossible to get the number A. For example, this is N is, and this one also Cn, and this palladium.
Yeah, that's what I want to hear.
Yeah.
That's what I want to hear. 그러겠지. So you see that if there is no coordination, he will have a Cn double bond. So, but not double bond. So she has a C and the single bond peak and this peak. So that is an evidence that this imine peak has been converted to this enamine peak through this palladium. 곡선 동의 안 하라고. 왜?
이중결합이 생기면 픽이
CC 이중결합.
CC는 어쨌든 이중결합은 전자를 주는 쪽이기 때문에 일렉트론 볼트가 작아지거든요. 이쪽 NH 표시해놓은 거 보면 작아지는 부분에서 숄더가 되게 크게 있는데 왼쪽은 쪼개서 숄더를 분해했는데 오른쪽은 쪼개서 분해를 안 해놓고
그리고 이 아모늄 섞여줄 수 있겠지. 그리고 이 아모늄이라는 것은 이게 팔 네 개처럼 됐다는 거예요. The one that you have shown is ammonium, Abu.
Yeah.
The one that you have shown is ammonium. This is due to another evidence that you have a coordination, because after coordination, it looks like the nitrogen. If you focus on the nitrogen has 4 bonds. Although 3 is equivalent, 1 is a coordination bond. That's what you want to say. So from this ammonium, there is this ammonium peak. The N plus charge demonstrate is due to this formation, the coordination. You understand?
Yes.
So it makes sense. It makes sense that you have a coordination between this functional group with this palladium, but still very difficult for me to understand from this one whether you have a complete or the coordination ratio. But I don't think it will be very difficult.
I took the SEM and the EDS mapping. The EDS mapping, we can know the element arrangement and element percentage, and I also.
No. I think that will be very difficult. XPS도 가능하니 그러면? 이게 코디네이션 된 정도를 지금 여기서 아모늄 피크나 그걸 가지고 쫓아갈 수 있는 그런 저 CN 저거 세퍼레이션 시키면 가능해?
3번 빠지만 보면은 그냥 그걸 줄할 수 있을 것 같은데.
다 따라서. Yeah, I think so. This is your last pick, right?
Yeah.
Last slide, right?
Yeah, last.
Okay. So yeah, I appreciate it. So I think you can 국수가 한번 더.